Well, good morning, good afternoon, I should say, everyone. I'm David Tilbrook, and I'd like to welcome you to the second seminar of the AIP Theoretical Physics Seminar Series for 2021. I should start by acknowledging the people of the Ngunnawal Nation on whose land we are located here at ANU, and also, of course, to the traditional owners of lands around Australia. We would also acknowledge their elders, pay our respects for their elders past, present, and emerging. So this series of seminars has been made possible on behalf of the AIP by the organising committee and by Murray Batchelor in particular, who have volunteered their time to identify topics in theoretical physics that are interesting and topical, not just to theoretical physicists, but to physicists more generally also. As I mentioned, this is the second seminar in the series. The first was a really interesting talk given by Professor Tracy Slattier from the Center for Theoretical Physics at Massachusetts Institute of Technology. And she talked about the existence and properties of dark matter and how dark matter might interact with itself and some of the particle physics that might be involved with dark matter. If you missed that or you'd like to watch that again, Tracy's talk is now available on the AIP YouTube channel. There should be a link to that via the AIP homepage, but it can be a little bit hard to find. So the best way is to just use your search engine and do a search using the search term Australian Institute of Physics YouTube. That will take you to the AIP YouTube channel, and you can look at Tracy's talk there. Today's talk is on an equally interesting subject, and as everyone would be aware, and it is inspired by recently announced results from Fermilab following earlier work that had been done at the Brookhaven National Laboratory in the US back in the early 2000s, 2003, 2004, I think, something like that, which appear to pose a challenge to the standard model. To that effect, it gives me a great deal of pleasure to introduce today's speaker, which is Professor Raymond Volkas from the University of Melbourne. As some of you will know, Raymond has made very significant contributions to a wide range of topics in theoretical physics. He's credited, for example, with the discovery of the neutrino oscillation-induced neutrino asymmetry mechanism and the development of the mirror matter model, which has applications to the dark matter problem and to neutrino physics more generally. But Raymond's also made a contribution to other diverse areas of theoretical physics, from the very big, such as neutrino emissions from the galactic center, to the very small, the persistence of quantum coherence in the presence of strong environmental coupling, a topic which is dear to my heart. And that's just to name a few. So without any further delay, please like to very warmly welcome Raymond. Over to you.
Thanks very much for the intro, David, and thanks to Murray and the AIP for this kind invitation, and very happy to see 50 or so people tuning in. So as David already said, there's been some exciting announcements from experimental collaborations over the last couple of months that are pointing towards, but not yet proving, that muons are behaving differently from how they should according to the standard model of particle physics. So that's why there's a question mark at the end of my title, and I'll walk you through what the evidence is and what we know, and you know what we hope to find out in the near future. Okay, so my talk is structured as follows. I'll first briefly review the standard model of particle physics, just to tell you what, to remind you of the current state of play in terms of us understanding elementary particles and their interactions. Then actually, before I get to the misbehaving muons, I want to review existing proofs for physics beyond the standard model. So we already know that the standard model of particle physics is inadequate, and the misbehaving muons, which I'll turn to in part 3 of the talk, are simply adding to that. Then in 4, I'll talk about possible implications for physics beyond the standard model that would explain the misbehaving muons. that's an extremely large topic, and I'll only just touch on it, just giving a couple of biased examples, and then I'll talk a little bit about the future. So any talk on the standard model begins with a graphic like this, which shows you all the elementary particles constituting this theory. So we have fermions here on the left, quarks, which are strongly interacting particles, and leptons, charged leptons, and the neutrinos, which are not strongly interacting. And these come in three families. So one of the puzzles of nature, which we still don't understand, is exactly why this neutrino charged lepton down-type quark, up-type quark pattern, is replicated a couple more times. Sorry, lost control of my mouse. And these fermions, which constitute the material particles, interact via the exchange of spin-1 bosons, gauge bosons, the gluons for the strong interaction, photons, and the Z and W bosons for the weak interaction. And then since 2012, we've known about the existence of an elementary spin-0 particle, the Higgs boson, and I'll review the role that it has in a later slide. Okay, so in short, the standard model is three families or generations of these spin-1/2 quarks and leptons interacting through the three known non-gravitational interactions. And then there's the Higgs boson, which is responsible for mass generation. Mathematically or theoretically, the standard model is a gauge theory. So it's a mathematical generalization of the gauge invariance of Maxwell's theory, where the gauge group is this more complicated thing, SU3 cross SU2 cross U1. This direct product of groups is telling us that there are three independent forces here, which are the strong, weak, and electromagnetic. The SU3 part describes the strong interactions mathematically. The SU2 cross U1 part describes a combined theory of what we call electroweak interactions. The degrees of freedom of the standard model are quantum fields. So these are functions on space-time, and they are operators. And these operators create and annihilate particles and antiparticles like quarks and leptons. Then, in order to define the theory, we have to specify how the various field operators representing all the elementary particles, exactly how they transform under this SU3 cross SU2 cross U1 gauge group. And by specifying those representations physically, that encodes how these particles interact under the strong and electroweak interactions. So what you see in the lower part of the panel is a certain notation that we like to use in particle physics that summarizes the representation or multiplet content under the gauge group. So the first entry, I'm just looking at the left-handed quarks for the sake of the example. The first entry is telling us what representation under SU3 these fields transform by. The second entry relates to SU2. And then this is the abelian charge, and it's called hypercharge Y here for the standard model. So the fact that the left-handed and the right-handed quarks are transformed non-trivially as a triplet under SU3 is telling us, is encoding the fact that the quarks feel the strong force, whereas the leptons, left and right-handed leptons do not, they're singlets under SU3. Turning now to SU2, we see that the left-handed quarks and left-handed leptons are doublets, whereas the right-handed versions of them are singlets. So this is telling us physically that left-handed quarks and leptons couple to the W boson, but right-handed quarks and leptons do not. And the fact that there's this difference in the way that left and right-handed quarks and leptons interact, in fact, it's maximally different because the right-handed ones don't interact at all, and the left-handed ones do. That is encoding the experimental fact of parity violation, a difference between the interactions of left and right-handed fermions. And it is this fact that actually prevents us simply writing down in the theory fermion masses, because fermion masses require a coupling between right-handed and left-handed versions of the same particle. And you can't do that if they transform differently. And this is why we need a Higgs boson. And then electromagnetism is embedded in a subtle way. It's partially in SU2 and partially in this U1 of hypercharge. It has a certain generator. And then there's also a Z boson as well, which is an aspect of the weak interaction. And then this pattern, as I've already said, is repeated 3 times for reasons we have yet to understand. All right. Then the next part of it is the rules of the game say that because we have a gauge symmetry, a local symmetry, we have to introduce spin 1 particles in order to make the theory gauge invariant. And the way this is done is to extend the space-time gradient to what is called a gauge covariant derivative by adding a second term that depends on these gauge fields or these spin 1 force-carrying particles. And you have one of these fields for every generator of the group. And there's a parameter here which is going to play an important role in this talk, little g, which is the coupling strength. And one of the predictions of gauge theories is that this coupling strength is universal. So all quarks, for example, coupled to gluons with the same strength. This is called universality. And it's a breakdown of universality that may be indicated in some of the experiments, just to foreshadow that. So anyway, we get from this by the group theory, there are 8 gluons. Then the weak interaction has, the SU2 part has 3 spin 1 gauge bosons, and then there's the hypercharge one. And then the photon and the Z are certain linear combinations of W0 and B. And then finally, amongst the bosons, there's the Higgs doublet of spin 0 particles, and the representation assignment of this thing is driven by the need to give masses to the W and Z bosons, which are known to be massive, not to give mass to the photon, of course, and also to give mass to the fermions, the quarks and the leptons. And yes, I want to emphasize that this gauge force involves a universal coupling strength. It's a clear prediction of gauge theory, including the standard model. Now, the way you having all those ingredients, we then define the theory by writing down the most general renormalizable Poincare and gauge invariant Lagrangian, or Lagrangian density, consistent with the aforementioned field content. And here it is in all its glory. Oops. There are all sorts of terms here involving kinetic terms for gauge bosons, involving Yukawa interactions between fermions and Higgs bosons, self-interactions of Higgs bosons, gauge interactions of the fermions with the various force-carrying particles. I won't go through it all. Suffice it to say that an artist called Peter Kennedy, a Melbourne artist, was so impressed by seeing this equation that he decided to render it into a multicolored neon, and this formed part of a big exhibition at the NGV a few years ago called Melbourne Now. So it is truly a work of art, literally, the Standard Model Lagrangian. The final thing to review about the Standard Model is spontaneous symmetry breaking, especially, in particular, electroweak symmetry breaking. So this is where the electroweak part of the gauge group is broken, in a sense, to a subgroup, and that subgroup is the gauge group of electromagnetism. So what happens is that the Higgs field, the scalar field, has a potential energy whose minima are displaced from the origin, so they occur at non-zero values of the Higgs field. And so then what happens is that nature chooses to sit at one of these points along this circle of minima. It doesn't matter which point it sits at, but it's got to sit at one of them. And then what we do is we consider nature to be the nature we live in, to be a small fluctuation around this minimum. And so we have to rewrite the Lagrangian in terms of fluctuations around this displaced minimum. And when we do that, the full symmetry of the theory is not absent, but it's hidden. And this is the way we generate masses for the charged fermions and the W and Z bosons. And in the standard model, neutrinos remain as massless fermions, and the photons and gluons remain as massless spin 1 particles. All right, so now let me explain why we know that this wonderful theory, which explains a lot of data extremely well, is nevertheless incomplete. It's incorrect to say it's incorrect. The right way to put it is that it is incomplete. So the first empirical proof that the standard model is incomplete comes from the discovery of neutrino oscillations, which implies the existence of non-zero and indeed non-degenerate neutrino masses. So the standard model of particle physics does not have mass terms for neutrinos. And while we know that the neutrino masses are really tiny, they are definitely non-zero. And so the theory has to be extended to account for that. All right, so this is the first empirical proof that the standard model is inadequate. There are a whole bunch of theoretical qualms also about the theory, not exactly inconsistencies with data, but just inadequacies. There's a lot of parameters in the standard model Lagrangian, as you saw, all these various very physically important things like quark and lepton masses, coupling strengths, Higgs mass, and so on. There are hierarchies in these observed masses, and we don't understand why, but there seems to be a pattern, or you can imagine there's a pattern there, and we'd like to understand those hierarchies. The neutrino masses are really, really small, probably about 1/10 millionth that of the electron mass. And so it looks like neutrino masses are special. So why are they so tiny? There's something called the strong CP problem. I've mentioned the three families. We don't understand that. Something called the hierarchy problem. And also gravitation is notably absent from the standard model construction. Okay, in order to get to empirical proof number 2, we have to expand our horizons to include cosmology and astrophysics. So we've got to bring gravity into the story at some level, but not quantum gravity, just classical gravity. So what we do is we write down an action which minimally couples the standard model fields, the fields that make up everything, to general relativity. So it's done through this action, never mind the details. This is the Ricci scalar. This is just the Einstein-Hilbert action. This is the cosmological constant term. It describes dark energy at the moment, as far as we know. And then the metric also appears in the standard model Lagrangian and tells us how the various particles couple to gravity. So if you want to do cosmology, you've got to do GR, but for many other astrophysical applications, Newtonian gravity suffices. And that's a limiting case of this, of course. So the second empirical proof, sorry, I have a very touchy mouse. The second empirical proof is what Tracy talked about a couple of weeks ago, and that's the evidence for dark matter. And she will have surveyed all of this diverse and self-consistent catalog of bits of evidence for, strong bits of evidence for dark matter. In fact, the evidence is incontrovertible, as I say. And there is no viable dark matter candidate in the standard model of particle physics. And yet this stuff, whatever it is extremely important cosmologically and astrophysically. By mass density, there's about 5 times as much of it. And so that's a really big mystery. And that's why we have a center of excellence for dark matter particle physics. We want to understand what sort of particle or particles constitute the dark matter. So again, the standard model needs to be extended. And then it's something I sort of whimsically call empirical near proof number 2.99 rather than 3, because it's not quite rigorous, but it's almost rigorous. And that's the cosmological matter-antimatter asymmetry. So the universe is full of matter, and there's very little antimatter around in the universe today. And what little there is sort of has known production mechanisms in large measure. So the question is, given that matter and antimatter are almost identical, apart from having opposite charges and so on, why is it that the universe today is full of matter rather than sort of being a dilute mixture of matter and antimatter, equal amounts of matter and antimatter, and then in a sort of sea of radiation? So, in the early universe, just after the Big Bang, through pair production, of course, there should have been both matter and antimatter around. And what must have happened at some point in the evolution of the universe is that a very small 1 part in 10 to the 10 actually preponderance of matter over antimatter happened, and then eventually all the antimatter annihilated and gave us radiation, and all the stars and galaxies and you and me are formed from the matter left over. So this is also a fundamental problem. So why is it just a few fussy words about why it's a near proof. So it is still technically possible for this asymmetry to be an initial condition at the Big Bang. But this scenario is very bizarre. It would lead to a very fine-tuned universe in more than one sense, not just the asymmetry between matter and antimatter, but also our universe is observed to be spatially flat today, come through very clearly from the CMB results. but in standard hot Big Bang cosmology, this requires extremely fine-tuned spatial flatness at the Big Bang. Okay, so cosmologists consider this to be a very fundamental problem, and that's how inflationary cosmology was born. It was designed in part to fix this problem. And if inflation is true, or something like it, then having the matter-antimatter asymmetry as an initial condition is simply not viable, because once inflation ends, there's a lot of particle creation, and that would wash out any pre-existing asymmetry. So the alternative to taking this as a proof of the need for new physics is a bizarrely fine-tuned initial condition at the Big Bang, both in terms of spatial flatness and then this very funny 1 in 10 to the 10 asymmetry in matter over antimatter. Okay, so these three things are the pillars at the moment of empirical proofs of physics beyond the standard model: neutrino masses, dark matter, and the matter-antimatter asymmetry or baryogenesis. The recent evidence is adding to this picture and suggesting new inadequacies of the standard model. And it's interesting that muons are involved in one way or another in all of this emerging evidence. So I will now turn to that. All right, so muons have been exciting from the moment they were discovered in the 40s. So humans were expecting the pion to be discovered because there needed to be a force that held protons and neutrons, especially protons, which repel each other electromagnetically in nuclei. And so they were expecting pions, and what instead was discovered was a muon, which didn't fit the bill. And famously, Rabi was given this information while, having a Chinese lunch or something in New York, and he said, "Who ordered that? We didn't expect that. We wanted the pion. Why did we get the muon?" And the existence of the muon is still a mystery. We don't know what it's for, but it's certainly there. So anyway, the muon is the second most massive charged lepton, the E, the mu, and the tau. These are kind of like copies of each other, but with ever higher masses. The fact that the masses are higher, so for the muon, it's about 105.6 MeV, about 200 times more massive than the electron, and the tau is really quite massive, and we'll talk more about the tau later on. Because the muon is massive, it's unstable. It decays under the weak interaction. It has a lifetime of 2 × 10⁻⁶ seconds, which, at first sight, you might think, well, it's therefore difficult to do experiments with it, but or to have beams of it, but that's not true because of relativistic time dilation, and so you can produce, useful muon beams, and I'll talk about some of those experiments later on. And just to review, the muon decays most of the time into an electron and a pair of neutrinos. And the way you produce muons at accelerators is from pion decay. So pions decay predominantly to muons, and you can get either sign, either the muon or the anti-muon, depending on which charged pions you tune in. All right, so now let me turn to the most recent announcement, which is about the anomalous magnetic moment of the muon. So first of all, an intrinsic spin-a-half particle in general has a magnetic moment, mu. And it's parameterized through this linear relationship between the magnetic moment and the spin angular momentum. And there's this parameter little g, which is key. So it's a dimensionless number that defines the magnitude of the magnetic moment. Now, for elementary particles, the simplest theories, like Dirac theory, and also non-relativistic quantum mechanics, but with minimal coupling thrown in, predicts actually that G is equal to 2 for elementary spin-a-half particles, that is non-composite particles like electrons, mu's, and taus. Not true for composite particles like protons and neutrons. However, these two approaches, Dirac and Pauli, are not exact. The exact approach has to rely on relativistic quantum field theory. And in that full theory, of which the standard model is an example, there are calculable corrections to this dominant G equals 2 result. And these corrections are called G-2, or the anomalous magnetic moment of the relevant particle, mostly electrons and muons. And that's what the recent measurement is all about. Okay, so first I want to review how this G-2 of the muon and the electron are actually calculated. Sometimes we talk about G-2 and sometimes about A mu. They're just related by this factor of 2. So, so this is a big business. It started back in the late 40s with Schwinger, who computed the first QFT correction to G equals 2. And that comes from this particular diagram here involving an electron, which emits a virtual photon and a virtual electron, and that virtual electron couples to an outside photon, an external photon. This is a correction to the coupling between the electromagnetic coupling between electrons and photons. And famously, he computed that A mu is equal to the contribution to A mu to G-2 over 2 is alpha over 2 pi in quantum electrodynamics, which is about 10 to the minus 3. The state of the art for, and there are different classes of contribution to G-2 of the muon or electron. The first class I'm talking about here is just from QED, quantum electrodynamics. So the state of the art is due to the leadership of Kinoshita, and this has been calculated now up to 5 loops. So in terms of perturbation theory, that's to order fine structure constant to the power of 5, whereas this is fine structure constant to the power of 1. And these are really, really state-of-the-art brute force calculations, kind of a very impressive and amazing and exhausting piece of work. So just to show you some of the QED diagrams involved, just for your amusement, here are some 2-loop graphs. So this is higher order of perturbation theory. This is order alpha squared. 3 loops, ever higher order, 72 diagrams by this stage. Moving on to 4 loops. Moving on to 4 loops, there are now 891 diagrams. Moving on to 5 loops, there are now 12,672 diagrams. And all of these have been computed by Kinoshita and collaborators. In addition to the QED contributions, there are also contributions from the weak interactions. These have been computed to 2-loop order, and the dominant effect from 3-loop contributions has also been worked out. Here are the sort of different classes of diagram that are involved. You see W bosons, you see Z bosons, and so on. And finally, there are contributions that care about strong interaction effects. And this is where all the discussion lies. And this is a really critical part of the whole story. So there are the 2 most important classes of hadronic corrections are called hadronic vacuum polarization and hadronic light by light. This one I won't talk about much because it's a small effect. Let me concentrate on this one. So what we have here is a virtual photon exchanged between the incoming and the outgoing muon lines, and as it propagates between those 2 muons, it fluctuates part of the time into hadronic stuff. And this hadronic stuff is strongly interacting, and so you can't use perturbation theory to understand what's going on inside this blob. And this is the dominant source of theory uncertainty in G-2. We're talking about a very small effect here, but the calculations are now very precise and the experiments are very precise, and so we need to understand how to do this calculation, even though it's hard. All right, so there's a big story about these hadronic vacuum polarization effects for G-2. And there are 2 methods being pursued by the experts, and I'm not one of them, to compute it. One is a data-driven method, so it uses dispersion relations and something called the R ratio. So this is saying, let nature do this calculation of these non-perturbative effects for us, and then let us use well-established theory to incorporate those effects into the computation of G-2. And the second approach is ab initio. So this is purely within theory, and you just put quantum chromodynamic strong interactions on the lattice. You use a big computer simulations and you just brute force do a computation. So two different approaches. Let me go to the R ratio method, this data-driven method first. So the well-established theoretical principles it's based on are mathematical properties of the scattering matrix, analyticity and unitarity, and the optical theorem. And these things combine to produce what's called a dispersion relation, whereby this hadronic contribution to the photon propagator is related to something you can go and measure, which is the scattering cross-section for electrons and positrons annihilating into hadrons. Annihilating into hadrons. So the idea is you take this from experiment and then you use this well-established theory to tell us what this contribution to G-2 from hadrons should be. Just to show you the kind of mathematics it involves, there's something called the G-2 theory white paper that came out last year. It's basically all the relevant theorists getting together and systematizing and agreeing on all the calculations. This is just the dominant contribution. This is LO means leading order. Then there's also next to leading order and next to leading order. This is just the dominant contribution. And you have to compute this integral. This factor here in the integrand is what cares about this thing that you measure, which is the cross-section of electrons and positrons annihilating to hadrons. And then you feed it into this integral with this wonderful function, and you get out the contribution to the anomalous magnetic moment of the muon. So let me now show you properly what the cross-section looks like. It's a very famous thing in the annals of particle physics because it kind of summarizes the history of particle physics in many ways. You see the Z pole, you see various resonances which correspond to the discovery of different kinds of quarks. There's the discovery of the charm quark. This is the B quark. Anyway, these are the kind of data you have to feed in to this data-driven method. So here's a summary table from the white paper. So first of all, we have the old experiment from Brookhaven, 20 years old now, and this is the experimental value multiplied by 10 to the 11 for G-2 of the muon. And then it summarizes various different computations of hadronic vacuum polarization at various orders from the data-driven method and also from lattice. You see you get various contributions here. Let's look at this part of the table, which summarizes everything. So the dominant contribution to G-2 is from QED, and you can see the number here. The weak interactions contribute quite a small amount, you can see, compared to QED. But notice that the hadronic vacuum polarization contribution is relatively large. It's really quite a lot larger than the weak interaction contribution. So this is why this is very important, whereas hadronic light by light is very small. So you add them all up, and this gives you the total standard model value as decided upon, as agreed upon by the white paper collaboration. And so you see a number, and that's the number you have to compare with the experimental measurement, and there's a discrepancy. And the discrepancy has at the time of writing of the white paper, which was last year, had a statistical significance of 3.7 standard deviations. So in particle physics, we like to claim a discovery when an anomaly becomes 5 sigma. So 3.7 sigma makes us very, very interested without yet causing us to claim a discovery. Okay. All right, so now let's turn to some experimental matters. So the Brookhaven experiment, E821, which was completed 17 years ago. Now here's a picture of the experiment. It's a relatively small one by particle physics standards, but very, very complicated and still a very significant effort. So here's a plot here's a plot of the difference between the experimental measurement and the standard model theory prediction as a function of date. Here is the Brookhaven result with the error bars. And here is how the standard model theory evaluations got better and better as more and more calculations were done. And as of sort of last year, this discrepancy had ballooned out to 3.7 sigma. The way the experiment is done in sort of schematic form is like this. You produce protons, they hit a target, which produce pions. As I mentioned earlier, the pions decay into muons. The muons are little bar magnets, so they spin around. You put them into the storage ring, which has a very precisely determined magnetic field, and they circulate around the storage ring, and as they do so, they also precess around the magnetic field, and you measure the precession angle by looking at the direction of the decay electron that you get when the muon decays. And what you look at is the highest energy electron in the muon decay, and that momentum is correlated with the spin direction of the muon. And in that way, you can measure the precession accurately, and hence also the anomalous magnetic moment. Obviously, there's a lot more to the story here, and I'm not qualified to say it. You need an experimentalist. This is very exacting work involving very precisely known magnetic fields and all the rest of it. Just as a bit of light relief, sometimes some fairly bizarre things need to happen in order to do an experiment. So let's now turn to the Fermilab experiment. So Brookhaven's over here in Long Island, and Fermilab here near Chicago. And so we wanted to do, the community wanted to do another G-2 experiment to test the Brookhaven result, right? Because it differs from the standard model by quite a significant amount. So in order to save money, rather than build a new storage ring, they transported the old BNL one from Long Island to Chicago. But this thing is so big that they couldn't take it by road. So instead it went by ship around Florida and then up the Mississippi, and then eventually arrived in Fermilab to pre-pandemic reception of a large number of people. Here you see it coming along on a big truck. And here is what the new experiment looks like. It doesn't look very different from the Brookhaven one, but apart from the storage ring, everything has been improved. The magnetic fields have been improved, all the instrumentation and so on. Okay, so this is a summary plot of the state of play. This comes from a collaboration called BMW, which is a lattice gauge theory collaboration. So let me now turn to the lattice gauge story, which I haven't talked about yet. So what we see here on the horizontal axis is this hadronic vacuum polarization contribution to A mu. And what's plotted on the vertical axis are different theoretical groups which have done this computation. And in order for the standard model to agree with experiment, the computation would have to come out at this value of 720. So the red points here are this data-driven R-ratio method. And you see that the three of them are consistent with each other with fairly small theoretical error bars, and they're quite discrepant from the measurement. And so this is what's driving the discrepancy. In green are various different lattice calculations. You see the error bars are rather large compared to the R-ratio method. And so this has simply not been competitive yet with the R-ratio method. But BMW now claim to have done a lattice calculation with rather smaller theoretical error bars. And you can see annoyingly that their central value comes exactly in between the R-ratio determination and the experimental result. The rest of the lattice community has to reproduce this result before really we will believe it. So a burning issue in the field is whether or not BMW is correct, okay? All right, ignoring BMW, this is the current state of play with the new Fermilab measurements. So first of all, Fermilab corroborated the Brookhaven measurement. This is their current result with current error bars. You can see the error bars are similar to Brookhaven at the moment, but they'll decrease in the future with more statistics. The central values are well within each other's error bars. So Fermilab confirmed the Brookhaven result. And because they are consistent with each other, it's legitimate to combine the two data sets, and this gives you the combined experimental average with smaller error bars. Compare that to the standard model prediction, which excludes the BMW calculation, and now the discrepancy has increased to 4.2 sigma. So this was the big announcement, and the excitement was, first of all, that the Brookhaven result has been vindicated, and secondly, that the statistical significance of the discrepancy went up. All right, so now let me turn to another new result, and another new result that was announced this year. We're not going to be talking, this is not about G-2, this is now about different things. And the new result announced this year, which I'll review in a moment, combines with some older results to point to other kinds of anomalies. And these are anomalies in B-meson decays, and they are suggesting a violation of that very fundamental property of the standard model I pointed out, which is the universality of interaction strengths, and in particular, the universality of charged lepton interaction strengths. So first of all, let me review for you what a meson is. So a meson is a bound state of a quark and an antiquark by the strong interaction. They're bosons effectively. And the B-mesons here are those that contain a bottom quark. So depending on what the other quark is, you get a charged one or a neutral one. There are also D-mesons, which have charm quarks in them rather than bottoms. And then there are K-mesons, which have strange quarks in them. Okay, and of course the antiparticle states of these as well. So another anomaly, and this is the one that became stronger also this year, is called the Rk anomaly. So Rk is the following. It's given by this ratio of decay rates. So gamma is a decay rate of a B-meson to a K-meson and a muon-anti-muon pair, and that is compared to the same decay mode with the muon replaced by an electron, okay? This process involves a B quark to S quark transition. It occurs at one loop order in the standard model, and here is the diagram. A B quark emits a W and a virtual top, and then when the virtual top and W recombine, they recombine as an S, and then the electron, positron or muon-anti-muon pair are produced from a photon or a Z that is radiated off the top. Okay, now, in the standard model, this ratio should be 1 because of the universality, the same interaction strengths of muons and electrons. The muon is more massive, so there's a bit of phase space suppression of the numerator, but it's really negligible. So we expect this ratio to be not exactly 1, but very, very close to 1. But there's an experiment at CERN called LHCb, which is dedicated to precise measurements of B quarks. And their new result is this one down here. And you see that their central value is different from 1, it's 0.846. And the experimental error bar makes the discrepancy between the standard model prediction and the measurement a little bit above 3 sigma. So not as dramatic as the G-2 anomaly, but still very much gets us interested. And it's also important that as time has gone on, this LHCb anomaly has not gone away. And it's slowly increasing in statistical significance. And muons are implicated in this as well. So it could be that there's something going on with muons that makes the numerator smaller than you expect in the standard model. And that's why LHCb measure 0.85 rather than 1. This would be a violation of E-mu universality. The idea is that there might be additional interactions beyond the standard model that are not universal between muons and electrons. A very kind of similar one is called RD and RD star. The star here just is an excited state of the D. This is a probe of universality between tau charged leptons and either electrons or muons, or both, depending on the experiment. In this case, the process in the Standard Model proceeds just at lowest order of perturbation theory, just as a weak decay, actually. This time, because the tau is rather more massive than both the electron and the muon, there is a phase space suppression of the numerator. Okay, but that's entirely calculable. And here's a summary of both the Standard Model prediction and the experimental results. So this plane is RD, so this is where the decay happens to unexcited Ds. And the vertical axis is RD star, that's where the decay happens to an excited D. The Standard Model prediction is represented, Standard Model predictions are represented by this black cross. Now, a number of different experiments have measured one or both of these ratios. Babar, an old experiment at Stanford, Bell, LHCb, and Bell has a number of different measurements. The average of all of the measurements is given by this red ellipse here, and that is quite discrepant from the Standard Model prediction. Notice, however, that there are issues to do with the self-consistency of different experimental determinations, especially between the most recent Bell measurement and the old Babar measurement. So this really needs new experiments to come along and really clarify the situation. And that will happen. LHCb will contribute, and Bell 2, which is now running, will also contribute in an extremely important way. And so over the next few years, we expect this situation to be resolved. But again, on the face of it, there's some evidence here for a discrepancy with the Standard Model and a violation of universality. All right. Okay, so now let me quickly turn to implications for physics beyond the Standard Model. First of all, let me talk about the magnetic moment. So although the disagreement in one sense is small, it starts at the 7th significant figure, in another sense it's large, because the discrepancy is about twice the size of the weak interaction contribution. So the idea is that there's some new physics represented by this blue blob, and that is more important to the magnetism of the muon than the well-known weak interactions, which involve, W bosons, which have a mass of 80 GeV. It's a one-loop effect. And it's sort of striking that the discrepancy is larger than this, which in some sense is a bit surprising because, the new physics here would involve particles that have got to be considerably more massive than the W and the Z, probably. They're not inevitable, but probably. And so the fact that this new physics contribution is bigger could be considered a surprise, but that's the state of play. All right, there's a nice paper involving people from Monash that came out recently, which summarizes all the new physics possibilities. So here they are. These are just generic one-loop graphs that involve new scalars, that's an S, new fermions, that's an F, or new vector bosons, that's a V. And these are just different topologies that you can invoke in various different beyond Standard Model theories to try to explain the anomalous magnetic moment of the muon. And there are many, many beyond Standard Model possibilities. This is a 100-page quasi-review article, and see that article for a comprehensive summary. I'm just going to go through 2 or 3 possibilities, completely biased by involvement from the University of Melbourne. So the first one involves work I was involved with 30 years ago, which is a certain kind of Standard Model extension involving a second type of Z boson, which we call a Z prime. So this is a kind of short-range fifth force. It's mathematically special for reasons I won't go into. It's a gauge boson that couples to both muons and taus with this minus sign in between. So in terms of the Atheron et al. Topology, it looks like this, except the fermion F here isn't new. It's just the muon itself, and this is the Z prime. And here is a plot in terms of the in the mass of the Z prime and coupling strength of the Z prime plane. And this green bit here, which involves a relatively light Z prime. This parameter space here doesn't violate any existing bounds, other experimental bounds, and can explain G-2. I like to point this out, even though it's a bit self-indulgent. this is just a plot of citations to our work. And you can see that in about 2012, interest really took off. So sometimes one has to be extremely patient. Another possibility that I was involved with late last year, early this year, involves the fundamental mystery of why all of these charged lepton masses, apart from the top quark, are sort of surprisingly small in some sense. There's a fundamental mass scale in the Standard Model, the Electroweak scale, which has a value of about 250 JeV. But all these particles have masses which are much smaller than that. And it could be the reason for that is that these guys pick up their mass not at tree level, not at the leading order of perturbation theory, but at higher order through more subtle loop effects, quantum effects. So we examined that. We examined the possibility that we looked at models where the muon mass is generated at one loop level rather than at tree level in order to explain why the muon mass is so small. And what we noticed is that any theory of that sort of origin, non-standard origin for the muon mass necessarily contributes something to G-2 of the muon. And here we have a plot in a certain model. I won't explain everything here. It's just a parameter space of a coupling strength and a mass in the model. And the wide area is parameter space that is allowed. And this gold band here is the subset of that parameter space that can explain the G-2 anomaly. So it could be that the G-2 anomaly is telling us something fundamental about the generation of muon mass. That's just one possibility amongst many. Okay, and then you can contemplate combined explanations for different anomalies. So here I'm going to talk very briefly about combined explanations of G-2, these flavor universality anomalies, and also why neutrino masses are so very tiny. And again, it could be that they're just generated at a very high order of perturbation theory. This is work I've done with my students and former students in S, John, and Julia. There are things called leptoquarks, which might exist, not in the standard model, but they might exist. Leptoquarks are bosons. They're coupled directly to a quark and a lepton. No such thing in the standard model. The spin 0 ones are classified here in this table. I won't go through all of these quantum numbers here. But anyway, you can work out what all these things would Yukawa couple to. And it turns out that a couple of them can individually explain the G-2 anomaly. One of them can explain the ID star anomalies, and another one of them can explain the Rk star anomalies. And so one bit of work we did was we combined S1 with S3 and were able to explain all of these anomalies, as well as providing an explanation for why neutrino masses are so tiny. Again, it's just one theory out of many. All right, and just giving you some examples. All right, so let me now turn to my penultimate slide, I think, which is about the future. So the Fermilab experiment on G-2 is ongoing, and it wants to halve its error bars in about a year, and eventually by the end of the experiment have them 4 times smaller than now. In addition, a second experiment is being constructed in Japan at J-Park, and the goal there is to have eventually a similar experimental error to the Fermilab experiment. So this will again be a cross-check of the experimental results. And this theorist, Aid El-Qadra, a couple of years ago, summarized the situation, saying that if the central values don't change, then the anomaly will hit 5 sigma just from the improvement in the experiment. And if we can compute the hadronic terms more accurately, it's conceivable to get it to an 8 sigma discrepancy, which would then really, really be a discovery. In terms of the flavor universality ratios, this yellow little ellipse here is what Bell 2 expects to be able to achieve at the end of their life in the mid-2020s. So you can see really small error bars. And if this yellow ellipse is displaced from the standard model prediction, that could constitute a very statistically significant discovery of new physics. LHCb is also planning to reduce their error bars very significantly in these flavor universality ratio measurements. So the future is bright, and we don't have to wait very long. Like we don't have to wait 50 years like we did for the discovery of the Higgs. It'll all happen in the next few. All right, so to summarize, we have 3 empirical proofs that establish that the standard model is incomplete. Strengthened recently by a host of, this is strengthened by a host of theoretical shortcomings of long standing, but the misbehaving muons are currently indicating further evidence without yet proving that there is additional evidence for physics beyond the standard model. But a bit of time, a few years, and a lot of hard work on the part of mainly experimentalists, but also theorists computing G-2 will tell. And if the hints are confirmed, then actually that will be a really epical discovery. So thank you very much. I'll stop there.
Well, thank you very much, Raymond. That was a fascinating talk. If people have questions, there's one question queued up. And then if people could put them in the Q&A section, that would be great. Peter Price asked initially if you could just clarify what the acronym BMW stands for.
Budapest, Marseille, Wuppertal. So they're just theorists from those institutions.
Right. So if anyone else has any questions, they can pop them in the Q&A panel and we can read them out. But if I could maybe kick the questions off. So the graph that you showed, which showed the difference between the experimental results and the results from standard theory, also showed a nice difference between the results from lattice gauge theories and standard theory, although of course the lattice gauge theory, because of its limitations, tends to be characterized by larger error bars and so forth. Do you think there's anything significant in the difference between the lattice gauge theory approaches and the standard data-driven approaches? Do we regard that as another proof that something's missing in the standard theory?
Right, very, very good question. So first of all, before BMW came along, the error bars on the other lattice calculations didn't allow you to conclude anything because they were consistent with the R ratio determination as well as with the experiment. Now, if it does turn out that the lattice computation is different from the R ratio computation, that by itself, independent of any experimental measurement of G-2, would be pointing to something fishy, because there's nothing wrong with the R ratio method as far as I understand it. There's nothing wrong with it. So if there is a discrepancy between 2 different methods that should be giving you the same answer, then that could also be a pointer to physics beyond the standard model. If it turns out that the lattice determination is bang on the measurement, then the new physics doesn't contribute to G-2 of the muon, but there has to be something that explains this discrepancy. And there are papers about this already. It would imply a different kind of tension between precision measurements in experiments and standard model theory, different from the G-2 tension, but still a tension. So, there's the beginnings of a no-lose theorem here in some sense, but we really need to know, what the truth is with these lattice calculations, and I think we're all waiting for the rest of the lattice community to get its computations to having similar error bars to BMW.
Oh, great. There's another question here from Ulrich. Apologies, Ulrich, if I pronounce your surname incorrectly. Agid, is it? I'm not sure. He writes, you reminded me that it is only for point-like fermions that the G-2 prediction is valid.
Yeah.
Are there theories that try to introduce composite muons to explain the G2 anomaly?
Right. Thanks, Ulrich. So I'm not up with that, even though I did my PhD thesis a long time ago on things like composite muons. I'm not aware of any recent works that try to explain it with composite muons. It may be possible. I simply don't know. But certainly that would certainly be worth understanding if that's still viable.
Right. A question from Sandy Dance, who wants to know a little bit more about the comparison of the muon result to electron and tau lepton results. They, particularly the tau leptons, is there any evidence that they also display anomalous magnetic moments, or are their half-lives just too short, or what's
right? Also a good question. So first of all, with the tau, the magnetic moment of the tau has not been measured really. It's a very unstable particle. It's hard to do this measurement. We don't have a storage ring for taus. Even with time dilation, they don't live long enough. There are other ways, just through examining very precisely the electromagnetic interactions of taus and accelerators, that future measurements should be able to actually measure the tau magnetic moment. So that's something to look forward to. But at the moment, the experimental results allow a whole range of possibilities, from a standard model value for the tau G-2 to something very different from the standard model. The electron situation, so this is a very astute question. So the electron G-2, which is also computed extremely accurately like the muon one, is more sensitive to actually the precise value of the fine structure constant. And at the moment, and this is a developing thing, so this is another thing that happened earlier this year, you can measure the fine structure constant very accurately in atomic physics. And cesium and rubidium in particular have been used. And there are two different experiments using these two different elements. And those two experiments provide different values for the fine structure constant, and they're very different. They're not compatible with each other, okay? And so depending upon which one you believe, you get G-2 of the electron to be either less than its standard model value or more than its standard model value from experiment, okay? So it's very confusing. We need to settle this experimental issue of what is the value of the fine structure constant in order to know if there's any new physics in G-2 of the electron. My student Ines Bigaran wrote a nice paper, a few months ago, where the indication was that there were anomalies in both muons and electrons, but they went in opposite directions. And in order to get that to happen, you needed very, a special kind of new physics. And she worked out a way to do it, which seemed really interesting. And then along comes this new rubidium measurement, and suddenly the discrepancy is on the other side, if there is a discrepancy at all. So it really is very unclear what's going on with electrons at the moment.
Right. Question from Bruce Yabsley here says, in a seminar last week at CERN, Isidori presented all of the other muon-related anomalies as being consistent with a single new physics explanation, and the G-2 being due to, in brackets, something else. Do you think that's reasonable? Do you have any feelings about that?
So Bruce, was that a vector leptoquark that he was talking about?
I could activate Bruce if I can find him on the list quickly.
I imagine that's what he was talking about.
Bruce Labsley, there you go, Bruce, you can ask a question.
Ray, can you hear me now?
Yes,
Okay.
very good.
Yeah, it was the vector leptoquark, the U1 in that.
Yeah. It's been known for a while that if you want one leptoquark to do all the flavor universality stuff for you, you can use U1. That's different from the U1 of groups. It's just
I understand.
Name for a certain particle. So phenomenologically, that's okay. From a theoretical point of view, writing down a complete, consistent, renormalizable theory which has that vector leptoquark in it of a sufficiently low mass is a challenge. And Isidori, has been constructing elaborate theoretical schemes to try to do that. So while phenomenologically it seems like a very simple explanation and a very minimal one, when you actually look at how you would write down a theory that contained that thing, life gets much, much more complicated. So, I would say, so I would leave it at that. Phenomenologically, it looks very simple. Theoretically, not so simple.
So it has to do with which sort of complications you regard as reasonable and.
Yeah, well, it's a spin one particle, so it needs to be a gauge boson, and it needs to be a massive one. So you need an extended gauge group like a Patti-Salam SU4 or something like that. Sorry to get technical for the non-particle physicists. And you need to spontaneously break it. You need to do all these things.
Yes.
And you need to avoid experimental constraints of one sort or another. So it's quite a business to actually make a theory where that works. So I would say phenomenologically, it's very elegant. Theoretically, it's complicated. The scalar leptoquark case, so spin zero leptoquark case, is theoretically looks less appealing in some deep sense, but the theories are much easier to write down.
Right. Okay, thanks. That's clear.
Question, this seems to be more experimental from Cobus Labascu or Labascane. I'm sorry if I got the name wrong. Is it possible to use elements other than rubidium and cesium?
Not an expert. You must ask an atomic physicist. That's a very, very good question.
Yeah. And finally, at this point, these anomalies, if real, look rather ad hoc, is the comment made from Archil. I.e., why a muon, not an electron? Do you see these as a sign of a bigger flavor puzzle?
Well,
the pattern of masses and mixing CP violations, etc.
Indeed, it could well be. At the moment, we're just being driven by the data in terms of our model building. And for sure, there are certain ad hoc things that you need to do. You need to switch off, you need to turn on couplings to muons, but switch them off to electrons, say. So you need some flavor structure in there. So I would say if these anomalies are real, they probably do point to something fundamental about flavor symmetries. It's a bit too early. I mean, it's in the back of my mind to think about that. But we're probably not at the point yet where we want to devote a lot of time to it, because we want to see these discrepancies really confirmed. And then we will have a lot of interesting and deep thinking to do about the nature of the three families and flavor physics in general. Completely agree with you, Archil. But you can't ignore the data. The data is saying this. So.
All right, that appears to be all the questions. I might just ask one more question, and then we could wrap up. You would be aware, I'm sure, of the CERN Muon E experiment that has been proposed, or that they're carrying out. As I understand it, that's an attempt to measure more accurately the higher order hadronic leading order corrections. Do you have any comment about that, or do you think that that's going to provide some more useful data? Or
so which experiment do you mean?
But there's a CERN experiment called the Muon E experiment, which they are proposing. I don't know very much more about it than that. I know that it attempts to be a new approach to get information about the hadronic leading order corrections for the muon G-2.
Oh, okay. Yeah. Right. So look, I vaguely heard about it, but I must admit I'm not up to speed on that. Yeah, I mean, I guess you want to measure this R ratio more and more accurately, so that you can feed the correct thing into that integral you have to evaluate in the data-driven method. I guess that's what it's all about. So I certainly think that is a useful thing to do. Yes. All
right. Well, thank you very much, Raymond. That was a really fascinating talk. For those people who are interested, we will upload this talk, as we do with Tracy's, to the AIP website, the AIP YouTube channel. And as I said, you'll be able to see that when we get it loaded. Just do a search term on Australian Institute of Physics YouTube, and that'll take you to the AIP YouTube channel. So thank you once again, Raymond. If I can ask everyone to give a virtual round of applause. I've just got to find the way you press the clap button, and I'll just do it manually.
Thank you very much. Appreciate you.
Thank you very much, Raymond.
All right. Cheers.
Thank you.